Bismillahirrahmanirrahim. Assalamu alaikum dear students, welcome back in lecture 01, example 04. This is example 04. One of the most important example this is because here we are going to analyze a triangular section. The section is right here. You can see here this section. This is a triangular section and the data is here. We have FC prime 3000 psi. We have 3 number add bar, right? And the yield strength is 60 ksi. This example is presented to demonstrate the general use of strain compatibility and section equilibrium equations for any type of beam section. This is, you can say, an example which will elaborate how to use the strain compatibility equations and how to use the equilibrium equations. Like you can see here in the section that most of time we assume that we are using that C equals to T here, and here is the lever arm. So if, as we already discussed this for a rectangular section, if the section is changes to any irregular section, so how you can use these compatibility equations of equilibrium. So let's start. Let me bring this figure right here because I have to align this with the top fiber. I have drawn this, right, these lines. This line representing the top compression fiber and this line representing the bottom tension fiber, and this is my neutral axis, right? And this red line is basically represented the lower portion of the compression stress block. The stress block is given right here. You can see this is A, and the width of the triangle is this one is A, and the depth is beta 1 times C. We have to find out this A. The area of this stress block, it is already given to us, that is here you can see A square divided by 2. Now the effective depth is given, that is 21.5, and the overall depth is 24 inches. And similarly the overall width is 24 inches. Right, this is the overall width of the beam. So this is an equilateral triangle, you can say, right? So here is the area of steel, that is 3 number add bar. So how much it will give us? 3 number add bar, we have to multiply this with the 3 times 8 divided by 9, right? So from this we will find the area of steel, right? So let me find out the area of steel right here. Area of steel will be 3 times area of 1 bar. Area of 1 bar is number of bar divided by 9 square. So from this you will get 2.37 square inches. So this is the area of steel, 3 number add bar, and we know all the data, right? So here we see the stress distribution. This is the equivalent rectangular block of the stress, right? The total depth is A, which is right here, and now this is a triangular shape, right? So in the triangular shape, we all know the centroid of the of a triangle lies a distance of 2/3 of A. 2/3 of A, right? This is very important to understand that it will be 2/3 of A from the top. From the you can say this is a triangle. So in the case of a triangle, we all know, right? If you have a triangle, right, in this shape, so the centroid from the bottom is 1/3, and from the top it is 2/3 of the total depth. RH. So you must remember this from your engineering mechanics. Now the lever arm is LARJD. It is also denoted by JD. So it is how much your lever arm in this case. Remember, in this case it will be D minus 2/3 of A, not A divided by 2. In the case of rectangular beam, this is A divided by 2, but here it is 2/3 of A. Now we know T is A is Fs, right? And we also know C here, that is 0.85 FC prime into BA. So in the case, this is the most important case, right? In the case of a rectangular section, right, in this one, right, so we know the area of this section, that is, we know this C is what is 0.85 FC prime into BA. But this is for a rectangular section, right? When we see the stress distribution diagram or block, so this is my stress distribution block, right? Let me draw the 3D view. This is my stress distribution block, right? So this is the width of this section B, right? And this is the depth of the section, which is A. So the area of this section, is so simple. We just multiply B with A, right? And we multiply this with the extreme fiber stress, which is 0.85 FC prime. So this gives us C, total compression. But here in this case, it is not a rectangular section, it is a different section, right? So let me try to draw the 3D view of the rectangle. So it will be look like in this shape, right? It will be look like in this shape. So here you can see this is my stresses, and here is the total compression, right? Total compression C, which is acting from the top, right? This is total depth, which is given, that is A, right? And this distance from the top at which the centroid or G of the section lies, where total compression is acting, is 2/3 of the total depth, that is A. So what we need here, we need the area of this triangle, right? We need the area of this triangle, and the area of this triangle will be is given to us, that is A square divided by 2. So this is the area. Now we need to find out the C value, which is acting at the centroid of this triangle. So C is 0.85 FC prime times BA, but here we would use this one, A square divided by 2. So we need A, right? Because this is a review question, and in a review question we need the value of C and the value of A. We need these two terms, right? We need these two terms. So how to determine this? This is the question. So using the first assumption, that let's say F is equals to Fy. This is the first assumption, right? Now using the assumption, we will find out the tension force, right? We will find out the tension force. The tension force is simple, A is times Fy. We know the value of A is, that is, we calculated 2.37 times 60 KSI So from this we will find 142 kips. Remember, tension is the force, not stress. Okay, so that why the unit will be in kips. Now using the equilibrium condition, right? Using the equilibrium condition, if the section is in equilibrium, we can say C will be equals to T, right? So we will easily find that T is 142 kips, right? If we convert this into pounds, we can multiply it by 1000, so it will be 142,000, right? Pounds, 142,000 pounds, right? Now the main objective of finding the C is to find out the value of A. Now we know the value of C, that is 0.85 FC prime into A square divided by 2, as we already discussed it right here. In this case, C will be equals to 0.85 FC prime into A square divided by 2. So from this, right, from this we will arrange all these terms and we will find out the value of A, right? Just plugging the value of 142,000 multiply by this 2 will be multiplied with to the left hand side, and these 2 will be shifted in denominator, so 0.85 FC prime and taking square root, right? So from this, if you use your calculator, make sure that you are using this value is 3000 psi, right? Because this value is in pound, right? So from this we will got the value of A, that is 10.6 inches. Now it is easy for us to analyze the rest of the question, because we find out A, we can find out the value of C. C is what? A divided by beta 1, and beta 1 will be 0.85 because the strength of the concrete is less than 4000. So dividing A value divided by beta 1, we got the value of C, that is 12.4 inches, right? So once you got this, we can easily find out the value of strain epsilon S will be equals to epsilon T, because there is one layer of steel, and here we have D minus C divided by C times epsilon U. So plugging all the values, we have D value, that is 21.5 inches. We know the value of C and we know the value of epsilon U, that is 0.003. so what we got from this, we got 0.00220, right? This is my epsilon T value. Now I have to find out the value of epsilon Y, which I have to compare with this value. So my epsilon Y value will be Fy divided by ES, that is modulus elasticity. So 60 divided by 29,000. Let me calculate this value. What is this value? Here we are using the calculator, that is 60 divided by 29,000. So we see the value is 0.0020. Now we will compare this value with the strain value, right? So we got 0.0020. So as we see clearly that epsilon T value is more than the epsilon Y value. This means what? This means the assumption is right. This means the assumption is right. Fs equals to Fy, and this means what? This means the steel is yielding. Means the steel is yielding, and the section is a tension control section. Tension control section, right? Section is a tension control section, and yes, section is a tension control section, and we can easily now find out the value of Mn, right? The value of Mn, that is, in this case it will be Mn equals to As times Fy times here is lever arm, that is d minus 2/3 of A. Write down noting this value, right? Because in the rectangular case this value is just A divided by 2, but in the case of triangle it is 2/3 of A. Now if you plug all the values in this equation, right, we know the value of A is, that is 2.37, we know the value of Fy, that is 60, right? We know the value of D, that is 21.5 minus 2/3 of A. We know the value of A, that is 10.6. So from this we got the value of 2060 pound inch. You can convert this into kef inch, divided it by if you multiply it with 1/12 times 1000, you will got your result in 171 kef feet, right? So here this is the way that you can check the value by using this kind of procedure. You can multiply this with the p-value, right? And the p-value will be, you see here that the epsilon t value is 0.0022, right, which is less than 0.005 but greater than the value of here you can see epsilon t value is more than 0.002, but it is less than 0.005. So we have to adjust the phi factor by using the equation 0.42 plus 83.3 epsilon t. From here you can find out the value of p value and then multiply that value with this 171. You will got your design capacity, that is MD. Now one thing you must make sure, I have not discussed this in the previous example, in example number 1, 2 and 3, that in a review question you can also check some other things, right? Some other parameters, some other parameters, right? Like you can check the minimum steel area, right? Whether the steel which are here we will providing, that is 2.37 square inches, because it is a review question. So we have to make sure all the ACI criteria, a number of ACI criteria that we can check it, but here we are just only checking the capacity. The other criteria, we know that A is minimum. ACI specifies a certain value of the minimum steel area, and I have discussed it in lecture 01 part 9, that your providing steel will be more than the minimum steel, but it should be less than the maximum steel. So you have to check it. This criteria is satisfied because the section is a tension control section, so this is already specified. But here, because we have to provide a minimum reinforcement, why? To prevent a brittle failure, right? I have discussed this completely and I have derived the equation for the AS minimum, right, for a beam, which I have already find out, that is 3 times FC prime under root divided by Fy, R, right, or the other limit, that is 200 divided by Fy. So I have derived this equation, I think so, in part 09. So from this we can find out the here the governing part is this one, right? Because if you multiply this 3, let me check it, 3 times the stress value, it will give me a value of 164, right? This is important, right? Let me write down here, noting 3 times FC prime, that is 3000. So if you use your calculator, it will give me 164.31 psi, and you can see from this is divided by Fy, but I'm not dividing it by Fy. Let me divide it by Fy, and here I have 200 divided by Fy. So here you can see this one will be more than that one. Okay, so here 200 and here 164. So this value will be more than that 164. So that's why I'm ignoring this part. I'm ignoring this one, and we will use this value, right? Because we have to choose the maximum value from the 200 divided by Fy, or from 3 into Fc prime under root divided by Fy, right? So using that value 200 divided by Fy and find out the minimum area of steel. So let us recalculate it. 200 divided by Fy, that is 60,000. Remember, you have to use 60,000 times BW into D. Here is the question: what will be the desired width of the section? Because this is a triangular section, although in a rectangular section it is clear to us that B is a uniform width we have, but in a triangular section we see here, as in this case, that here it is 24 inches, but as we proceed further, right, along the depth, we see the width is decreasing. Now the best assumption is that to use the average width, B average, right? But it is difficult to calculate the average width as well. Now, because this is important, that in which section the tension crack will be developed, and up to which depth these cracks will be penetrated into the section. This is very important. But here we are using a conservative value, right? We are using a conservative value. Let's say we are using BW, that is 24 inches, right? This is a conservative value because when we are selecting the value in the interior portion, right, at a certain depth, so that value will be less than this specified one. So if you are choosing a lesser value, it will give us a lesser amount of the S minimum. So if you are increasing this width, it will give us more area of steel, minimum area of steel, right? So that's why we are choosing a conservative value, that is BW. BW equals to 24 inches. So 200 divided by 60,000 into BW, that is 24. So let's see what will be the result. 24 times 21.5. It will give me a value of 1.72 square inches, which is less than 2.37 inches. So here the upper limit and the lower limit is specified, and we can say A is provided is more than S minimum, and it will be less than S max, because from the ductility this check is already okay, as we can see from epsilon S or epsilon T, right? But this is now satisfied, right? So this ends here, this example, and it is very important that how to analyze a non-rectangular section. If you have to face such example, you must be able to solve such an example. Thank you for watching. See you in next lecture.